So apparently this is the new thing, video. So I'm going to try and use it today to record a session on machine as a service. So this is a list of what we're going to cover today. I'm going to talk about setting up Kubernetes cluster using K3D. Once we get that up and running, I'm going to sit Tinkerbell in it. That's a particular MaaS solution out there. Once we stand that up, I'm going to add in some of my own data center config. So I have a little mini NUC here. We're going to use that as a demo. Once the config is set up in Tinkerbell, I'm going to hit reset on the mini NUC, and let's watch that come up. That'll be our system set up, crudely. After that, let's talk about GitOps and how we can actually formalize that a little bit more, and a little Easter egg at the end. So let's get going. Okay, first let's talk about our environment. So we're going to just run a couple of simple commands here just to give you guys an idea as to where I'm operating. ls USB release will give you an idea of the Ubuntu version I'm running, 2204. K3D is already installed, 546, and I have Docker installed, 2010-21. Now, K3D cluster list will list the clusters that are already created. As you see, we'll have none, and it uses Docker, and if you saw quickly there was nothing running from a Docker perspective as well. Let's create a cluster, simple cluster called my cluster, and you see how quick it is to actually set up a cluster under K3D. Under the hood, it's invoking K3S operations, which effectively spins up a cluster using Docker as the underlying infrastructure. You'll see here the list shows my cluster created, load balancer is true, that's important, we'll talk about that in a moment, and Docker PS shows you actually two containers are spun up. That might be interesting to you. The server LB is actually the traffic load balancer that's automatically created for default clusters. Now, just to show you that it's indeed a Kubernetes cluster, kubectl get all shows you what's up and running in what we've just created. So that's an example of just a simple cluster create. So let's get rid of it. Now focus on what we need for Tinkerbell itself, which requires a little bit more in terms of configuring K3D. Just to prove we've nothing here, at the moment list reveals nothing, and Docker PS likewise. And now I'm going to pull in a command and I'll talk a little about exactly what we're doing here. So we're going to create a cluster under K3D, and the first thing to note, which is important, is the actual name of the cluster, TK cluster. We're enabling host access. This is really important for the boots component to be able to intercept DHCP messages on port 67. That's required. And finally, Tinkerbell itself deploys its own load balancer, so we're going to disable traffic in this particular instance. So these parameters here will just remove traffic, the default load balancer, from the cluster we're about to create. Now you can see how quick that is. Let's take a quick look at what is created. Here you'll see load balancer is false. That's important, and you'll see only one container spat out from Docker PS. That's the container we're going to run Tinkerbell in. Finally, just to show you that it's indeed again a cluster, nothing special here. Kube system, the predominant namespace. So in essence, that is our cluster created for our environment. Next, we're going to focus on standing up Tinkerbell. Okay, so you'll see here from the git remote, that's the repository I've cloned, and the most important file in here, and actually the only file you really need to focus on is the values.yaml. This will configure Tinkerbell for you. TinkStack is a container, it's of type load balancer, and that IP address 112 is locally accessible to all our nodes in the system, so it's important that it's on the same subnet as what you're trying to configure. Choose what you want and lock it in, and as you can see in this values file, it's just replicated 3 or 4 more times. So this is to expose internal cluster services from Tinkerbell externally on that IP address. Additionally, you need to set the physical NIC that this particular kubevip load balancer is going to listen on. This is another view of how simple it is to actually change the difference between the upstream and what I've changed locally. As you can see, it's predominantly IP addresses and NICs, but what I'm highlighting here actually is that I'm also altered the hook image, which is the VM Linux that is used in the initial phases of the booting. Finally, you can adjust the command line arguments for that particular image. No mode set here just allows me to make sure I can have full visibility into the actual NUC as is booting on my lab here. These NUCs have i915 drivers, and sometimes I lose sight of a booting system. So with that values.yaml file created, all we need to do is leverage Helm to actually bring it up. So Helm dependencies build stack effectively cycles through all the subdirectories for all the microservices and pulls together a Helm YAML file which is applied. So we're going to the right to directory structure, loading it up. Charts are created here. We're going to set trusted proxy to make sure external IP addresses are visible internally, and then finally we're just going to kick off the build. So pasting in the Helm install command here. The most, I guess, important thing to highlight here is the namespace Think system. That's critical because you're going to be operating and configuring your data center a little later in the context of that Kubernetes namespace. So here we've just named it Think system, and that's what we'll use as we progress. And okay, kick it off. It's going to take some time because it's got to download that hook file, so we're going to fast forward and come back when it's all done. Okay, we're back again, and Helm install is now completed. As you can see, the system is deployed. That didn't take very long, but as I mentioned earlier, you could pre-download that hook image to make things a little quicker and just host it on a local server and point here your values file to that particular server. So let's take a look at the namespaces we've ended up with. Namespace, get all namespaces here will show you that the load balancer set up to that IP address I pointed out a little earlier, 112. So now that's servicing traffic internally from external parties. Think system, the namespace we created, is where our microservices for Tinkerbell are actually deployed in. Boots controller, Hegel server, and Rufio, and the stack itself, which is responsible for orchestrating the whole thing. For completeness, let's take a look at Docker PS. It shows we're still in a single container environment, and I'm going to exec in here into that particular Docker just to show you the directory whereby the local Nginx server actually serves out the VM Linux and the initfm, then the init ramfs images to booting clients. We'll use this directory a little later, but thought it useful for you to know that you can actually direct with it here. So let's configure our data center. I have a directory lab charts here where I have a sample data center setup, and it comprises of 3 YAML files, a hardware, a template, and a workflow. The hardware file is what we're going to focus on first. It effectively is agnostic to pretty much everything, and it's responsible for describing what your hardware looks like. Here we're calling it Mini NUC. It's an abstract name. We can call it whatever we want. What you'll also see here is that I've used the Think system namespace. That could also be set to default, and because we're going to apply the namespace later in our kubectls. This device has a disk, an NVMe drive. This is a YAML array, so we can put in multiple disks here. Abstract facility code on-prem. What's really important, however, in this file is the MAC address, because it uses the index key to identify this device, and it kind of wires everything else up together. We're going to service out via DHCP this IP block to this connecting device, so we're going to give it 203. And finally we're going to allow PXE. That allow PXE is interesting because we can actually differentiate between interfaces that are serviced via PXE and those that are pure, simple IP addresses. Here I have 2 NICs on this device, so I'm leveraging that to be able to give out 210 to the second NIC when it just does a simple DHCP request. Clear Linux.yaml is actually a description of our operating system. It's agnostic to everything and wired real-time via the templating mechanisms. Here using Kubernetes, device_1 is what will be pulled in when we apply this ultimately. What I'm highlighting here is the actual operating system particular to this YAML file, obscure name, but just take it that that's the operating system. Compressed raw image, and it's going to be serviced out in port 8080, which was configured in the original values YAML file. That's important, and what I really mean by that is you need to understand exactly the structure of what you're servicing out. So here I'm doing an fdisk on an abstract image file, and you'll see here I've actually got 3 partitions on the one I've chosen, which would ironically render this particular YAML file we're looking at as incorrect, because as you'll see P2 has identified the second partition to write that action, which is just writing a simple file out to disk, and that should be root. In fact, that should be P3 if I were to change the image URL to point to this particular image. So beware of that. We're going to do a docker exec here to show you what's inside in the actual opt-hook folder. You'll see a repeat of what we showed you a little earlier, but now what I want to do is I want to make this particular image available to external devices that are going to pull it, and to that effect I need to copy from my local drive here images, the particular Spring Valley sys dnet image into that /opt-hook directory. That'll allow Tinkerbell itself to service out and feed out that compressed image to requesting clients, and you'll see here doing an ls in the directory via docker exec. There it's populated in. So now we're ready, or the system is ready to service out that. Let's take a look at the other actions here. Write network d config is sysd network d, and you should recognize the structure of that particular network configuration. It's just setting up all interfaces en star to be DHCP, and finally BertCert is just going to write out the date that we commissioned this device onto the drive. Finally, this is what pulls everything together, the workflow, and it ties the MAC address to the identifier for the actual operating system you want to install. So that's the structure of our data center setup, and all that's left for us to do now is to actually apply it. So let's try and do that. Moved into the lab charts folder where these exist, and just to prove, just to show that it's unpopulated at the moment, I'm going to run a kubectl get on the hardware to see what Tinkerbell knows about hardware entities. As you see, there's nothing there, so now we're going to apply the hardware. It's a simple apply -f to the hardware, and we're going to rinse and repeat that with actually the template and finally the workflow. And we're going to just show you here the output, hopefully, of these particular kubectl applies. So let's run a get on that last one, and you can see I've called it WF1, so I'm targeting particularly the ID WF1 here to spit out what it knows. So here we're in state pending, so the system now is ready and set up to service a booting client. Let's do that next. So this is where we put things into motion, and in order to actually monitor it, we're going to set up some logs here, or actually monitor logs. So firstly we're going to take a look at the pods in the Tink system. and we're going to follow two particular containers. The first one is the Tink server that is responsible for the workflow entity. So here we're just going to do --follow on that and leave that sit, and then secondly we're going to observe boots. This will be a little busier. It'll show the actual DHCP and FTP traffic between the Tink service and a booting system. So we're grabbing the container IDs and we're using those to actually follow. So this 7 minutes is going to be quite slow, so you may want to fast forward on a few occasions, but right now in the background I'm booting up my NUC, and it'll take some time as it comes up via its BIOS. It's going to net boot on a particular interface, and once it starts firing out DHCP traffic, we should see some action in a couple of seconds now, whereby it's going to request an IP address and also get a request to service to install something on it. So just about now we should see the first signs of life from the device. Here we go. Boots has recognized that it is populated, in fact, with a MAC address as we configured earlier, ending in 3C, and it's going to farm out an IP address of 203 to that particular device, and it's also going to service out the iPXE file so that the device can actually proceed with what it needs. Next step after this will be the VM Linux download and the initRD download. That will come along shortly enough now, in about another 60 odd seconds. So let's hang around here or fast forward till you see a little bit more action on the screen. Right, here we should go. So now, what can we see here? A little bit more traffic. AutoPXE.exe is downloaded. The device phones home just to say, I'm here, do you recognize me? Tinkerbell verifies that and starts to service out the VM Linux, the NetFM RAMFS. What's happening on the device at the moment now is actually booting up the kernel and booting up rootfs, and once that, it'll automatically spin up a Tink worker on that particular device. That Tink worker, one of its first tasks is defined in the clear.yaml file. You'll see the top pane or top terminal here recognizes that, or presents us that the template file is about to kick into action. Stream clear Linux is now in state running. The device itself and the agent on the device is actually beginning to pull down that compressed file. The Spring Valley sys dnet. It's a compressed file, so the agent itself has to uncompress it on the far side, and once that's done, with the identified target device, it's going to actually push that image raw onto the NVMe drive. So that'll take some time again, about a minute or so, to burn the device down. So A little bit more action here. Now this is the slowest part of the actual process, but once the image is burnt down, you'll see that the workflow begins to move pretty rapidly on the top pane. So the remaining two actions, write network config and the bird cert, went from state running to success, and that actually completes the installation. We're going to take a look at bird cert now in a moment just to prove that we've installed this machine correctly. There's the date. So we're back with just to inspect our machine very quickly. We're going to SSH into the device we've just commissioned. If you recall, its IP address ended in 203. So let's see by SSHing into it. And let's take a look at that bird cert file and see what happened there. Right. So we're going to cat etc bird cert, and you'll see that just a moment ago this was written to. And for completeness, let's just do a version on subd. So there you go, Clear Linux installed on the device. Let's proceed. So next up, GitOps. We have our system up and running locally. Let's see if we can figure this one out. ArgoCD is what I'm using. That's the website here presented. So let's see what namespaces we have. We're going to create ArgoCD as it highlights, and okay, so this install at YAML is the default install, but we're going to make a slight adjustment to it here. I've downloaded it locally, and I'm actually setting up the service for node port, so that means that we can access it via a web browser on our local server. Here I've set in the type node port, and I've given it a node port ID. Let's quit out of that, and let's just apply this file instead and see what happens. So I'm applying it important to the namespace we've just created. Apply-f install.yaml, and that was quick. Right, let's take a look at what that gave us. Let's do get pods on the namespace ArgoCD, and you'll see a host of microservices running. But more importantly, we need to figure out how to actually get in via a website. So let's just get a more detailed view of the pods in question. I'm looking for ArgoCD dev server, and you'll see here it's node port, and there are the two ports exposed for HTTPS and HTTP. Let's grab that 30080 and see what that gives us. Up here on a browser, localhost, let's pop in that node port value. Okay, normal warning. Let's advance. Accept the risks. There you go. So login page. But what's the password, right? Okay. Back to the ArgoCD website. Let's just persist that session locally so we can get back to it handily enough. A couple of backslashes, and let's run a grep on this web page for the kubectl command to give us the secret key. So I'm searching for login here quite easily. There you go. Get the secrets. So we're going to pop that into our terminal and see what that comes out with. There you go, that obscure string. Going to grab the string. We're going to use that as a password. Back over to ArgoCD, popping that in. Admin is the username. And let's go. Okay, we're in. Simple as that. No applications yet, we'll get around to that. But while we're here, let's just change the password. So popping in that same string again, we're going to forget that easily. Let's go for our usual Shark Tank. Pop in the new password. Confirm it. At least that way we don't have to be continually going back to generate the code from the kubectl command. Saving off the password. Let's log out and log back in. Check that that's okay. Password inserted, and voila, we're in. No applications yet, but we're going to get to that next. And See if we can wire up via GitOps. Okay, moving on. Okay, let's wire this up. I'm in a data center folder here, so this is going to be a new location, but let's take a quick look first at how our system is configured. As you can see, I have residue of what we were doing earlier. Clear template, the hardware, and the workflow exist. So let's get rid of them. So I'm going to just run kubectl delete on these CRDs one by one, and we're going to clean down the system. It's important to note that these particular CRDs were applied from a different directory. We're moving now to upstream GitHub, and this data center directory I'm in at the moment is actually a git clone of something I'll show you in a moment. All those are removed. Let's just do a double check, and as you can see, running a git across all three yields nothing. Okay, so let's take a look at this directory. As I mentioned, it's a GitHub clone. Upstream in GitHub, I created this little project. I have Hawthorne, which is where I store my hardware inventory. I have pretty much what you've seen before, and inside the MaaS folder I've got workflows and operating system configurations. Nothing really has changed here. We're moving upstream to GitHub, so we start from that position. So I'm just giving you a quick peek into these files. You should be familiar with them at this stage. So that's what's up there on Git. But let's grab the Git URL. Let's see if we can get this configured in ArgoCD. So inside an applications, I'm going to create an application, name it an abstract name. My data center will be fine here. Project is typically default, and we're going to scroll right down here quickly and pop in the repository URL as git sync on head path. We're going to put just current path, and we're going to identify the Kubernetes cluster we want to apply this to. Now, this namespace is important here. Let's go back over and take a look at how our Kubernetes cluster is set up. What are the namespaces? So you should recall Think System is where we're operating in, both for Tinkerbell itself, but also for its configuration. So we're going to pop Think System in here, and we're going to get Argo to recursively go through subdirectories. Let's create. Okay, so I'm out of sync. Why am I out of sync? Well, so assuming Argo is pulled and synced with the Git repository, what it's actually showing to us here is the CRDs that it's showing a little problematic with, out of sync. So let's pick one, workflow one. Let's take a look at the diff. What's it seeing? ArgoCD. Well, there's nothing, and that's what it wants to move to in green. So that's what it's kind of highlighting to us. We are healthy. We're tempted to click sync, but let's go do that. Now that was quick, right? So we're synced, but what actually happened? It's showing we're all green across the board. Earlier we showed we were unpopulated in Tinkerbell. Let's grab one of those earlier commands and see what's there now. Voila, workflow 1 clear, state pending. So Tinkerbell applied that change. Let's see if it did it across the board. Let's take a look at hardware. Mini-Nook 1 is there. Let's take a look at our template. Clear is there. Okay, so it successfully did that, right? That was easy, right? Let's do perhaps something a little bit more complicated. Right, so your system is set up and you got new hardware. So let's try and add a new device. So I'm moving into where I locate my hardware inventory, and this is a bit of a hack, but it'll just show it in principle. So I'm just going to copy what I have Mini-Nook 1, and I'm going to create a new hardware inventory, Mini-Nook 2. Let's VI that, and let's just change some of the values. So all I'm going to do here is going to change the name. Again, these are abstract names. Mininuc 2. Let's see if we can find it somewhere else. There we go. And again. We also want to change the MAC address, and that's really important here. But just as we're scrolling through, this is the IP address. We're going to give it a different IP address. We're going to leave the gateway and net mask the same. Now, 3C here, I'm just going to abstractly change it to 2C. This is important because this is one of the keys that Tinkerbell itself indexes off. So it would probably balk if we gave it a second machine with the same MAC address, because legally that doesn't or shouldn't exist. Okay, so we've changed our file. We're going to add that to our Git environment by adding the file. We're going to put in a little commit message, so we've added a new piece of hardware. And we're going to push that upstream, and let's see what Argo thinks of that. So git push is going to push it up to that GitHub repository, and let's take a look in that repository, see if it turns up. Made my common mistake, going to the wrong directory. Here we go, Mininuc 2, 23 seconds ago added, and as you can see, it's taken up a new file with the changes we've made. Let's refresh ArgoCD. You'll see it's out of sync, so it's recognized some change. Mininuc 2 has popped in there saying it's problematic, something has to be done. So all this will be closed loop. We have an open loop at the moment, just for demo sake. But this would be automatically worked if Argo was configured such. So here we're just showing one hardware device at the moment before we do the sync. Here we're triggering the sync, and we're going to take a look at that afterwards. Going green on synced again, and now you'll see Mininuc 2 appears. So we've Git opted. Let's do describe, just to give a little bit more insight into the newly created hardware device, and here you recognize the changes in the IPs and the names. So that is GitOps working. Next, let's take a look how we can take this a step further. Okay, so this is the bonus section. Earlier I showed you how we had to upload our image into /opt hooked inside a Docker container, which is a little bit messy. I'm showing you the operating system template here, and you should see Dragonbox Hawthorne.local on port 81. So what we're going to do here, what I've done here is actually I've decoupled, created a little Nginx server, and I've actually set up DNS in my environment here. So I've set up a name server. So let's do an S lookup on Dragonbox. You'll see it returns 176 for us. So this is just showing you DNS setup. So if someone comes for that particular URL, it'll resolve. I've also Nginx set up, and inside in its directory I've created an image folder, and there I've populated in the actual image that I want to install. Here's my Nginx up and running, Hawthorne.local, port 81. We'll talk about that a little later. But here I'm just highlighting that we have an images directory where we can pop in vetted operating system images. And just to show this works, I'm just running a wget on that image that was earlier presented in the template.yaml file. This allows us to decouple from the Tinkerbell Docker incarnation, where we don't have to do a Docker CP into that /opt/hook. So we can manage two things separately. That's all, and hope you enjoyed that.